be discussing the life and death of a star. So first off, does any of you know the first step to the life of a star?
Protostar?
Ooh, close. That's not the first one. But that's the second one. I'll just draw it like that.
Close enough.
Yeah. Does anybody know the first step? Somebody else raised their hand, I know it. What do you got?
I'm going to go with fusion.
No.
Are you talking the actual star stage or what happens?
Yeah, from the very beginning.
We're talking how from when a star forms all the way up to when it dies. So fusion is when it's living, so that's about the third stage.
Alright. Anybody else? Starts with an N.
Big cloud.
Cool cloud blob thing.
Nebula.
Ah, there we go. I don't know how to draw that, so I'm doing
It's
that.
about like that.
Moving on.
Step 3 was fusion.
Right. I don't know how to draw that either.
Just draw a star.
With an F.
So you got an A, but you did great, but you got an F. Alright, what's next? Anybody? Any guesses? Anything? Let's go. Let's spitball here.
Yellow star.
No?
That's
A different color though.
Red
So,
star.
There you go.
right
Let's
here
move on to
we're
red
in
star.
life. Yeah, if red star.
You do have red. Thanks.
Red. Red.
More pink. Okay, so what we do is it begins with a nebula, right? Moves on to the protostar, and there's two different stages about how the star works, but you can go to either a red giant or red supergiant, correct? Then it moves on to the supernova or white dwarf. Okay. Sorry, there's a lot of different stages, but right now we're going to teach you the life and death of a star. Yeah.
Okay, so the life and death of stars. Prepared everybody? No. So we start with the stellar nebula. It's a star nursery, essentially. It's where all your new baby stars are born. They are ridiculously big. This one here is the Horsehead Nebula, and it's 13 light years across. And a light year is how fast light travels in a year. It's a ridiculously huge amount of space. The light traveling from the surface of the sun to here, the Earth, takes about 8 light minutes. So we're talking an incredibly longer time than that. So an incredibly larger distance.
Okay, so protostars. First guess of the day. So what happens with a protostar is in these clouds, basically knots begin to form, gas and dust begins to clump together, eventually becomes massive enough that gravity takes over and it starts to collapse inwards, creating massive amounts of pressure and heat. Eventually, when there's enough gas, that pressure ignites a new star.
Okay, so we're going to be talking about 2 different sizes of stars. We're going to be talking about sun-sized stars, and we're going to be talking about massive-sized stars. So we're going to start with sun-sized stars. So a star like our sun is going to burn through the elements. It's going to fuse hydrogen into helium, and it's going to keep working its way up through the periodic table until about carbon. And then after carbon, the star isn't going to be massive enough to start any fusion of any higher elements, so it's going to start dying at that point. And it's going to fuse through these elements for about 10 billion years. And our sun is about halfway through that right now. It's about 4.5 billion years old right now. So it's really old, but not in the life of the star. Then it's going to expand after fusing all of its hydrogen and starting to fuse helium. And every time it moves to a successive element, it's going to expand larger and larger. Our sun is currently this big. It is 0.01 AUs, and what an AU is it's the current distance from the sun to the Earth. It's a fairly large distance. When our sun expands to the largest it's going to be twice that distance. So it's going to be really huge. And then it's going to puff off all of its outer layers when it's done expanding all the way. And it's going to, I say puff, but it's rather violent. And it's going to become what's called a planetary nebula. About half of its mass is going to blow off, and it's going to be really gorgeous to look like. And this is an example of a planetary nebula. And I think this one,
God's eye.
this is the God's Eye Nebula. The core, what hasn't been puffed off, is going to contract into what's called a white dwarf. And it's going to be about the size of our Earth, but it's going to have half of the mass of the current sun. So it's going to be really dense. It's going to be really heavy. But it's no longer actually fusing any elements because it doesn't have the mass to actually do that. So all of the light and heat that's coming off of it is just left over from when it was still living. And eventually all of that heat is going to dissipate and it's going to blow away. And what's going to be left is a core that's mainly made of carbon and whatever elements manage to stay trapped in that core. And it's not going to be lit up anymore, so it's a completely dead star. And we call it a black dwarf because you can't see it anymore in the black of space. Because astronomers are amazing at naming things.
All right, so the next star we're going to talk about are blue supergiants. These are the fun stars. The ones you don't want to be around when things happen. So this is our sun, and this is an average-sized blue supergiant. So massive, massive, massive star. Star life, this is Regal. This is the brightest star in the Orion constellation. These stars, just like the sun, are a battle between gravity and nuclear fusion throughout its entire life. The only difference is that these large stars typically burn hot and fast, where our sun will live about 10 billion years. These suns or stars will only live in the millions of years because they go through their fuel so quickly. Depending on their size, they can actually go way past carbon and fuse up to iron in their cores, but they stop there because that's the cosmic equivalent of ash. They can't derive any more energy from that source. So just like the sun, they go into a red phase, but this is red supergiant phase. These are the largest stars in the known universe. If you see here, this is the sun, and this is a red supergiant. This is the largest star in the universe that we know of, VY Canis Majoris. If you put this, if the sun was the size of a basketball at the foot of the Empire State Building, this star would be half the height of the Empire State Building. It evolves when there's no longer hydrogen fuel in the core, just like the sun, and then from there it goes through layering each element. So here's the thing you don't want to be around for, called a Type 2 supernova. Basically, when the star's core hits iron, nuclear fusion can no longer counteract the force of gravity. Those explosions can't stop the star from collapsing in on itself. So if we count down from 3, 2, 1. In that time, that massive star you saw collapsed in on itself. All of it just collapsed in. And what happens is the electrical repulsion of the particles within the star's core don't allow it to get down to a certain point, so it repulses and explodes. It's one of the most powerful explosions in the known universe. We can see these in other galaxies, and sometimes they can outshine those galaxies in the night sky. If one were to happen in our neighborhood, it would outshine the full moon, and it would look like day during night. But what's really important about these explosions is that it creates every element in the universe heavier than iron. So everything around you was created in the death of a star. Any uranium, anything, had to be created in this explosion. It couldn't have happened any other way. So the really fun thing is a stellar mass black hole. Basically what happens is the leftover core is so dense that it warps the fabric of space-time. Nothing can escape this. Light can't escape it. You have to be going faster than the speed of light, which is a cosmological speed limit, so you can't really do that. These are thought to be the infant stage of supermassive black holes that are at the center of our galaxies. And basically, what happens is they believe they just feed on stars and gas and dust and planets until they become large enough that they sit in the center of the galaxy. And to complete the process, this is what's left over after the explosion. This is the Orion Nebula, one of the most photographed objects in the night sky, and it turns into a stellar nursery.
All right. Do you want are you going to questions?
Yeah, I think this would be really good. So any questions, anybody?
So how many stars are born every day? Do you guys know? Or is there a way
Like
to
in the
kind of-
universe, in the galaxy,
In both, whichever one has the best answer, I guess. I don't know.
universe, we probably have the best
Yeah.
answer. We don't really have like a good estimate. It would roughly be, they'd say about one a month, just because it takes so long for that
Yeah.
disk to collapse in on
I
itself.
think the general estimate is we gain about 10 stars every year, is about the estimate. And then we're losing stars too, so we end up with roughly a balance.
And then about 3 stars a year go supernova in our galaxy.
Can it make like a chain reaction? If one star explodes, can it make another star explode, or are they not
No.
close enough?
It will blow, like in a binary system where 2 stars are going around each other, it can potentially blow off some of the layers, but it doesn't make the star itself explode.
Yeah, because the star tends to explode because its mass just gets so heavy that it can't counteract gravity. All the fusion inside of it can't counteract gravity. So what really determines that is how much mass the star's accumulated. Do you have a question back there?
How do you see a black hole if it's black?
You can't.
It's kind of like how we see the wind. You don't see it, you see the effects.
We see the gravity around it, and we see a lot of, so light doesn't necessarily escape, but it does have ejection streams that come out of the black hole, and it's usually in the X-ray spectrum, and that's what we can see. And then with like the supermassive black holes, that's really how we found it, because we saw stars were going at incredible speeds at the center of our galaxy around something we couldn't see.
And then if you saw when he was showing the stellar mass black holes, it had a star and it was kind of warping into this. Yeah, that was there was a black hole in the center of that, and it was consuming some of the mass from its partner star. So that's one of the ways that we see them. And another way that we'll see black holes is we'll see what's called gravitational lensing. It basically warps all the space behind it so we can see stars behind it through where it is. Any other questions? All right, so we're going to end with the movie.
Yep.
Yeah, to finish up, we've got this video that we actually created ourselves from a compilation of pictures on the internet, as well as a few short videos and then some music that you might recognize as well. And it just kind of summarizes everything that we went over today, and we hope you'll like it.
That's it.
That's it.